Ladies and gentlemen, I would like to thank the SVC and the Technical Advisory Committee for inviting me to the SVC this year. It's an honor to open the high power EB session. I would like to speak about gas discharge electron sources, which are powerful tools for thin film technologies, as we will see on the next 35 minutes. In the first part, I would like to speak about hollow-cathode arc discharge plasma sources, which are basing on a low voltage electron beam. I will speak about motivation, principal characteristics, give some typical configurations, and speak about applications vacuum coating. In the second part, I would like to speak about EB guns, EB sources, which base on a high voltage glow discharge. Again, motivation, some setup and characteristic information, and application examples. At the end, I will summarize my talk. Okay, let's begin with the first part. The main motivation that we are using LVEB sources is plasma activated high rate evaporation, which is core competency of Fraunhofer FAP. In general, you are familiar with evaporation, so an evaporator is heated by, for example, by an electron beam. So it emits neutral non-excited particles which move upwards to the substrate and condense there, forming a coating. In case of plasma activation, we have a plasma zone between. So these particles, as well as the reactive gas particles, are excited, ionized, or dissociated. They gain additional energy, and the ionized particles are accelerated in the plasma sheath between the plasma zone and substrate. So at the end, the impinging particles have more energy, and one can improve layer adhesion by that. One can control the microstructure of the coating over a very wide range, as we will see later. It's possible to promote reactive PVD processes, and it's possible to use the high growth rates of EBPVD because also the film properties are sufficient. On the right side, we see a chart of the ion current density in a substrate over the deposition rate. As we know, for example, with sputtering, we can realize smooth, dense coatings with a slightly lower deposition rate. For EBPVD, the deposition rate is some decades higher, but typically the coatings are porous and columnar. In case one wants to have also these dense, smooth coatings in combination with the high rate of EBPVD, one can assume that we need the same ionization rate as for the low rate processes. And in order to achieve sufficient ionization ratio at the high deposition rate, one needs plasma sources which give ion current densities in the range of 10 or more milliamps per square centimeter. And this is true for vacuum arc discharges. And that's why we use such a plasma source for plasma activated high rate deposition. How does it work? The LVEB source, which bases on a low voltage electron beam, consists of a hollow-cathode tube, typically made from refractory metal or lanthanum hexaboride. And after ignition, we have an internal plasma in this tube, ions which reach the plasma sheath are accelerated onto the cathode tube and heat the cathode tube to high temperatures by ion bombardment. Consequently, electrons are emitted by thermionic electron emission, accelerated into the internal plasma, and maintain the plasma by collisions and ionization. In case such an electron goes through the plasma column without any interaction with the working gas atoms, they are reflected on the other side and reflected back into the plasma. So at the end, they will eventually collide with an argon atom, and the efficiency of such an electron and of the discharge itself is enhanced by that. A part of the electrons from the cathode wall or from the internal plasma move into the coating chamber towards the anode, and these are this so-called low voltage electron beam in the energy range of some tens up to 100 eV, and they form the technologically usable plasma. Here we see a nice picture of the plasma. On the left side, there is the hollow-cathode orifice. The LVEB comes into the process chamber, and in dependency on the pressure, the range of these electrons is higher or shorter. In our device, the hollow-cathode tube is surrounded by an annular anode and a solenoid coil, both positioned coaxially around the hollow-cathode. So by using such a solenoid coil, which produces a magnetic field which is axial in the hollow-cathode, we can drastically reduce the working gas flow rate through the hollow-cathode and ignite this discharge very easily by high voltage pulses within some seconds. Additionally, the low voltage electron beam electrons are transported along the magnetic field lines into the chamber to produce a large volume plasma. On the right side we see our device which has been already transferred in an industrial application. It can produce plasmas of up to 30 kilowatts. Yes. Typical characteristics is shown on this slide. The hollow-cathode is ignited at typically gas flow rates of 100 STCM through the hollow-cathode tube. So we have here a potential difference between cathode and anode in the range of 30 volts. When we decrease the hollow-cathode gas flow rate, which is possible by the magnetic field stabilization, we see that the cathode potential drops to large negative values. As a consequence, the low voltage electron beam electrons have enhanced energy in the range of 100 volts and more, which is the maximum of the ionization cross-section for typical process gases. And the consequence can be seen on the right side. We have measured the electron density by Langmuir probe measurements and by optical emission spectroscopy. Also, again, shown over the hollow-cathode gas flow rate. And especially at large distances, here for 125 centimeters from the orifice, the electron density is increased by several orders of magnitude when we go down with the gas flow rate through the hollow-cathode tube. So, and at the end, we even reach electron densities which are almost homogeneous between the axial distance from 30 to 125 centimeters. So we can really produce large volume plasmas and fill large volumes with plasma. Okay, now we need to know how it works. I would like to show some typical configurations. The most simple one is a single source configuration, so we just attach one such hollow-cathode plasma source on the cathode, the process chamber wall, or we can implement it into the chamber. So we see some electron density over the axial and lateral position. The hollow-cathode is installed at position 0, 0. As we go up with the process pressure, the electron density goes high as well, because the low voltage electron beam has more collision partners at higher pressures, so also the plasma density goes up. But due to the reduced range of these electrons, the decay of the electron density on the axis is also increased. On the upper right side, we see the electron temperature. It's higher for the case of lower pressure, and we even see in the low pressure case some last tail of the LVEB itself, represented by a higher electron temperature. A second configuration is the tandem hollow-cathode system. In this case, we have two such hollow-cathode plasma sources, which are installed face-to-face to each other, typically. But this position can be also changed. And they are combined by a common mid-frequency pulse power supply. So first point is that we can run two plasma sources with only one power supply. And the plasma is pulsed between, bipolar pulsed between the two hollow-cathode sources. Typical numbers are 1 kilohertz of cycle frequency and a current of up to 250 amps. We have the same behavior like for a single source configuration. As we go down with the hollow-cathode working gas flow rate, the cathode and anode potentials move apart from each other, so the the discharge voltage is increased, and at the end also the discharge power, which we can dissipate in the plasma volume. On the right side, we see the ion current density, again shown over the extra and lateral position. And we see that with decreasing the hollow-cathode gas flow rate, the ion current density goes up, and we can reach values up to 10-15 milliamps per square centimeter. A further configuration is the multi-jet hollow-cathode system, which we have developed together with the University of Virginia. It's used especially for actuating the so-called directed vapor deposition process, DVD process. We see the chart on the left side. An electron beam heats the crucibles and the material to evaporate them, and we have so-called discharge, the so-called carrier gas, which is blown with a supersonic jet. So this supersonic jet transports the vapor upwards towards the substrate, which reduces sidewards losses of the vapor. And we can even reach non-light of sight coding through this jet behavior. In order to activate, this plasma activate this process, which is necessary to get sufficient coating properties at these high rates, which can be achieved, there are 4 hollow-cathode tubes surrounding the crucible, and which coaxially activate this jet and the vapor. Here we see some pictures. On the ups, there's the crucible with the 4 hollow-cathodes. Here we see the 4 plasma columns generated by the 4 hollow-cathodes, which are again pulsed by a common power supply. And in case we start evaporation, we see the actuated vapor in the middle. We have the same behavior as we have seen in the previous configurations. When we reduce the hollow-cathode gas flow rates, the plasma power goes up, and we can increase the ion current density by more than order of magnitude again, and reach the values of 10-20 milliamps per square centimeters, which we had identified at the beginning as the interesting parameter range for plasma activated ePECVD. Yeah, and when we can configure 1, 2, or 4 hollow-cathodes, why not 15 or even more? In my last configuration, I would like to show this hollow-cathode array, which we have produced and developed for web coder, which were polymer webs with a width of almost 3 meters, are coated with alumina by plasma-activated PVD. So we have both evaporators which evaporate aluminum. We have oxygen as a reactive gas, and these plasma sources which activate the vapor. And so it's possible to get coatings which enhance the oxygen and water vapor diffusion barrier on this substrate, and also the coatings get chemically and mechanically more robust. This is an application for this is food packaging. Okay, so this was already the first application. So now we know how to configure and how to install this plasma source, and now it's a question how to apply this in vacuum coating. First of all, before we start coating the substrate typically needs to be pre-treated and cleaned from surface contaminations. And this can be done with the hollow-cathode by sputter etching. In order to sputter etch, we typically need ion energies in a range of several hundreds volts. So one possibility is to bias the substrate with such a voltage, or in case the substrate needs to stay on ground potential, the plasma source can be biased in the opposite range to increase the ion energy of the ions which impinge the substrate. And this has been done here in this example. The hollow-cathode, especially the anode, was biased by a power supply with 500 watts. So the substrate was bombarded by high energy ions. We see that the etching rate can be increased by the hollow-cathode discharge power, and there is no end. We can, the saturation has not been reached here. We could reach etching rates up to 15 nanometers per second, which of course depends on the material which is being cleaned. And so it's possible to clean substrates in an inline machine quite efficiently. Okay, and after cleaning, we can start the plasma-activated deposition process. I would like to show it an example of stabilized zirconia, which is a typical material for thermal barrier coatings on turbine blades, or also for electrolyte membrane layers in solid oxide fuel cells. The latter one was the background of the project, which is shown here. So we have the electron source, the electron gun, which evaporates the crucible. We have the LVEB source, which activates the vapor in front of the substrate, and also the oxygen, which is the reactive gas in this case. The substrate is installed on a radiation heater and in a holder, which can be moved over the coating window to be coated. Yeah, and this has been done with at pressures of half a Pascal, substrate temperature is 900 degrees, and at deposition rates of 40 nanometers per second we have been reached. I would also like to point out the emission monitor, which is important. We have recorded the optical emission of the plasma to control the process, as we will see later. First of all, I would like to show the effect of the plasma activation on the process. On the left side, we see an SEM picture of YC coating without plasma activation, typical columnar and porous structure. We have a quite rough surface. On the right side, we see the effect of the plasma. It's really a smooth coating. We have reduced the porosity remarkably, and we have a very dense coating here. The micro hardness has been increased from 5 to 20 gigapascals. The ion content density was 25 microamps per square centimeter. As already said, the deposition rate could be shown to be linearly dependent or correlated with the intensity of the optical emission from the plasma. The plasma emits light, and this is characteristic for the materials and the process itself, and can be used for for process control. Yeah, and due to this linear behavior, it's possible to adjust the deposition rate to have reproducible conditions in every coating run. Or what can also be done is that during deposition, I can integrate the optical signal and stop the process when I reach a certain integral value to be sure, so I can be sure that a certain coating thickness has been reached. And this has been done successfully in this project. So the next step was to automate this, to realize a process control loop, and this has been done here. We have our plasma-activated PECVD process, which emits the optical emission. This spectrum has been recorded with our spec control software, which also allows for peak detect to calculate intensity ratios, substrate background, emission, or have various mathematics. So we get some sort of actual value which is fed into a PID controller. The PID controller also gets some set value, and so the comparison of set and actual value leads to set points for the process itself. So this is given to our deflection control software, which we call wave editor, and so new power density, new beam power, or dwell times on the pools are calculated and realized by the deflection system. Also the feeding speed for the crucible, for the ingot, can be adjusted, and this influences the plasma-activated PVD process and changes the optical spectrum again, and so you can realize a control loop for the PVD process. We have done this again for YC. Now in our lab coater, we have a half-inch crucible to evaporate YC which is heated by EB gun of 60 kV and up to 10 kW. We have used a multi-jet hollow-cathode, which I have introduced some minutes ago, and we have here our OES harvesting system. The spectrum looks like that. We have the visible range. We have identified 2 lines for yttrium and zirconium to control the process, and the results can be seen here. On the left side, we see the process without OES control, so the EB power was constant. We had a quite remarkable fluctuation of the evaporation rate and consequently also onto the optical emission intensity, which we have recorded. So there's an up and down over the time of the optical emission, and this could be correlated also with darker and whiter stripes in the SEM picture. So we have regions where of higher and lower porosity. It's not a change of composition, but of porosity in the coating, correlated to higher and lower deposition rate. On the right side, we see the case with OES control. So we have maintained a constant optical emission, so also more or less a constant evaporation rate from the crucible. So we see that the optical emission indeed is more or less constant, and we could reach a quite homogeneous distribution of the grayscale in our SEM picture. Please ignore the cracks. In this project we did not improve the interface between the substrate and the coating. It was the main focus was on this control and OES control function. In case it's clear that when we control the evaporation from one crucible, we can also control the evaporation from several crucibles. That's the co-evaporation approach, and that we have done also. We have replaced this half-inch crucible by a crucible which has up to 4 separate evaporation pools, and it's possible to evaporate up to 4 different materials by jumping beam method. We have again used this EB gun with a deflection system of up to 100 kilohertz, so we can jump very fast between the pools and evaporate up to 4 materials at the same time. We have evaporated here nickel, titanium, and zirconium. We see here a picture of the 3 crucible and evaporation pools. Left side we see this crucible head with the 4 holes where the ingots can be fed into the separate pools and evaporation pools. We see the optical emission down there. It gets quite complicated because we have more and more materials, so all these peaks are there, but we could identify peaks for control. I don't want to go into detail, but because we have shown this on the last TechCon, but we could also use this OES control to control the position of co-evaporated coatings. Besides PVD, we can use this plasma source also for CVD processes, which I would like to show here at the example of high-rate deposition of amorphous hydrogenated carbon films. We have this plasma source, which we are already familiar with now. We have a gas shower to introduce acetylene into the hollow-cathode plasma plume. We have used sputter-magnetron to sputter titanium as a layer adhesion supporting layer before we started the CVD process. On the other side of the process chamber, we see a plasma monitor, which is energy reserved mass spectrometer to analyze the process. And this mass spectrometer showed us during the process a lot of different peaks. We see a lot of crack species, so the acetylene has been very efficiently cracked and dissociated in this plasma. And we see also species of we see molecules which have been again produced by correct species with meet each